Good day, students. Welcome to mathgoodserve.com. In this clip, we're going to be going over problems 1 to 5 of the 2008 AP Calculus AB multiple choice release questions. All right, let's take a look at question number 1. We have to find the limit as x approaches infinity of the ratio of this product of polynomials. Now, first thing you want to do is you want to identify what type of limit you're dealing with. This is an infinite limit since x is approaching infinity. Okay, so what we want to do is we want to find the leading term in the numerator and the denominator and compare their growth rates. Okay, if the numerator has a bigger degree, then the limits will be tending towards infinity. If they're equal, then you look at the ratio of the leading coefficients, and if the denominator has a bigger degree, the limit as x approaches plus or minus infinity will be 0. Okay, so how do we determine the leading terms for those two polynomials, upstairs and downstairs? We can simply multiply. If you don't want to multiply, you can basically look at the product of the terms with the highest degree in each factor. So we have 2x and negative x. So in the numerator, you have negative 2x squared, and in the denominator, we have x and x, and in the denominator, we have x squared. Okay, so let me just show you the steps. So we've multiplied out completely the numerator. When you pull out the numerator, you get 2x times 3, 6x, minus 2x times negative x, negative 2x squared, and then negative 1 times 3 minus 3 plus x, because minus times minus is plus, okay? So you FOIL it out. And then in the denominator, you do the same thing. Expand that. X times x is x squared plus 3x minus x minus 3. Okay, combine like terms. In the numerator, I will also write it in standard form. Okay, make sure that the degrees are in descending order. So we have negative 2x squared plus 7x minus 3. All right, so that's the numerator divided by, in the denominator, we have, what do we have? We have x squared, just combine the two middle terms, plus 2x minus 3. All right, so what we're looking at for is a limit as x approaches infinity of the ratio of these two polynomials. All right, now the question is, why did we write this in expanded form? What was the whole objective again? The goal is to identify the leading terms and compare their degrees. Okay, so if you look at the numerator, this is the leading term right here, the term with the biggest degree, that's the leading term. And downstairs, that's the leading term, x squared. Okay, at infinity, these two terms determine the growth rate of the numerator and the denominator. That's why we're focusing on them, because they have a higher degree. Okay, so this limit essentially reduces into the limit as x approaches infinity of negative 2x squared over x squared. Remember, if the numerator has a bigger degree, you're going to plus or minus infinity depending on the direction. If they're the same as this, in this case, you just take the ratio of the leading coefficients. If the denominator has a bigger degree, the infinite limit is always 0. Okay, so let's put this one here. The ratio of the leading coefficients, because even if you examine it, these two divide out, right? So we have the limit as x approaches infinity of negative 2 over 1. Final answer is negative 2. Option letter B is your answer. All right, let's take a look at number 2. We have to find the antiderivative of 1 over x squared dx. Now, this is a case where rewriting can really help you find the antiderivative. If you're thinking about the rule to directly apply to this scenario, you are going to run into some complications, okay? So you want to rewrite it so that you can easily apply the power rule for antiderivatives. Okay, so how do we do that? We have integral of 1 over x squared dx. So we're going to use the reciprocal property of exponents to do this, okay? So this becomes the integral. Now when you switch a term from numerator or denominator, or from denominator to numerator, the sign becomes the opposite. So x squared becomes negative x to the negative 2. All right, dx. Now what you notice is just by rewriting, it's very easy for us to use the formula, differentiation rule, formula for powers. So you have the integral of x to the n dx is what? This is x to the n plus 1 over n plus 1. That's the formula we're going to use here. So if we apply that to this case right here, we're going to have x equals x to the negative 2 plus 1 divided by negative 2 plus 1. Don't forget, anytime you have an indefinite integral, when the integral slides away, you add a c. All right? So let's simplify this. We're going to have negative 2 plus 1 is negative 1, x to the negative 1 over negative 1 plus c. And if we simplify this, this simply becomes negative x to the negative 1 plus c. Answer is option letter D. All right, let's take a look at problem 3. Now we have to find the derivative. This is testing our ability to accurately apply the differentiation rules and techniques. So we have x minus 1 times x squared plus 2 raised to the third power. Now, is it wise to expand this? The answer is absolutely not. You spend a lot of time expanding this, and then you run the risk of making mistakes. So what you want to do is ask yourself, is there a rule I can apply to a polynomial function presented in this format? What do we have? We have the product of two functions, a linear function and a composite function, a composition of a quadratic and a cubic. Okay, so since we have the product of two functions, what formula should we use? We're going to use the product formula. Okay, so this first function is u, and this second function is in its entirety, the composite function is v. And we remember that uv prime is equal to v u prime plus u v prime. Okay, so this is the formula we're going to be applying here. All right, so let's go ahead and apply the product rule here. So I'm going to set it up first before I differentiate. It's always good to set up your derivatives before you start differentiating to avoid getting confused in your application of the formula. Okay, so f prime of x is going to be v, which is x squared plus 2 raised to the third power, v u prime. So I'm going to write it as x minus 1 prime plus u is x minus 1 quantity times v prime. So we have x squared plus 2 quantity cubed derivative prime. Okay? All right, let's go ahead and differentiate. So f prime of x is going to be x squared plus 2 to the third power. Now, what is the derivative of x minus 1? Derivative of x is just 1. Derivative of negative 1 is 0, so it's just times 1. Plus x minus 1. X minus 1. And then what's the derivative of x squared plus 2 raised to the third power? Now, you got to be careful here. Whenever you're differentiating a composite function, you must apply the chain rule. Okay? So how do we differentiate that? In this case, let me just do some side work here. We have f of g of x, that is x plus 2, x squared plus 2 raised to the third power. All right, so the alpha function is f, which is x to the third, and its derivative is 3x squared. All right, the inner function is the quadratic, x squared plus 2 times its derivative, sorry, is 2x. So the chain rule basically says that you're going to differentiate the outer function evaluated at the inner, so I'm going to take this inner function and plug it in here, times the derivative of the inner function. That is the chain rule for you, okay? So let's go ahead and do it. So derivative of the outer function is 3x to the second power, evaluated at the inner function is 3x squared plus 2 raised to the second power. Okay, so that's f prime of g times what? Times g prime of x, which is 2x. Okay, now if you take a look at the options we have here, they are all nicely factored out. So we want to exercise our factorization techniques here to see how we can avoid taking unnecessary steps. Okay, because if we expand all of this, it might be a nightmare to factor. Now, if you examine this polynomial function closely, you will notice that we could factor out x squared plus 2. Okay, so this is to the third power, this is to the second power. So if I factor out x squared plus 2, I am going to have f prime of x equals x squared plus 2 quantity square. So I'll be left with x squared plus 2 times 1 is just x squared plus 2, right? Plus, let's see, x minus 1 times 3 times 2x is what? 6x. Okay? Simplify a little bit further. That should give us the final result. So we're going to have x squared plus 2 quantity square times, now I have x squared. If I distribute 6x with, well, let me just show you the steps so we don't get confused. X squared plus 2 plus 6x squared minus 6x. Okay? So your derivative, f prime of x, is x squared plus 2 quantity square times 7x squared, let me combine these two, minus 6x plus 2. That's your derivative. The correct answer is option letter B. All right, let's take a look at question number 4. Now, we have to find the integral of composite functions. If you notice, we have sine of 2x, a composition of a trig and a linear function, and then we have cosine of 2x, a composition of a trig and a linear function also. Okay, so since this is a sum of two functions, we can integrate them independently, okay, because you can apply the sum or difference rules to integration. Now, you can do this using u substitution. That is a formula you always want to use when integrating composite functions. Think of u substitution as a reversal of the chain rule. Okay. Now, there is another formula or a shortcut you can use for problems of this nature. That's what we're going to use for this problem. So this is what you want to remember. If you're taking the integral of a function, the composite function, where the input function, the inner function is a linear function, this is simply the antiderivative of the outer function evaluated at the inner function divided by m. Okay, this is due to the application of u substitution. So following this formula right here, we can easily see that the antiderivative of sine of mx plus v, remember this formula is applicable only to cases where the inner function is a linear function, all right, like 2x is a linear function. So the antiderivative of sine, the question most students ask is this positive sine? Is this going to be positive or negative? So we have cosine mx plus b over m. Now you ask yourself, it's easy to think going backwards. If you differentiate cosine, does the sign change? The answer is yes. So when you're integrating, the sign changes also. Okay? All right, now that's for sine. And then if you want to apply the same formula to cosine, cosine of a linear function, if you integrate that, you get sine mx plus b. That's the derivative of the outer function divided by m, the coefficient of x. Now, is this negative or positive? Ask yourself, when you're differentiating sine, does the sign change? The answer is no. So when you're integrating cosine, its antiderivative, the sign does not change either. Okay, so let's apply that here. So in this problem, we have the integral of sine of 2x dx plus the integral of cosine of 2x dx. This is the sum property of integrals. Now, if we apply this formula here, what you notice is m is 2 in both cases. So our antiderivative becomes the integral of sine is negative cosine 2x divided, okay, not times, divided by 2. Remember, when you're differentiating, you multiply the coefficient, right? Integral is the reverse of differentiation. So think division for integration and then multiplication for differentiation. Plus the antiderivative of cosine is positive sine mx plus b, which is just 2x, divided by m, the coefficient of x, which is 2. Okay, and then we can add that c, the constant of integration. We can clearly see that our answer is option letter B. All right. All right, let's take a look at problem 5, the last in this review installment. Number 5, now, if we're to find the limit as x approaches 0, 5x to the 4th plus 8x squared over 3x to the 4th minus 16x squared. Okay, this is a finite limit, so first thing we'll do is substitute. If we substitute the number that x is approaching into the polynomial functions, right here we're going to have 0 plus 0 over 0 minus 0, which gives us 0 over 0. This is an indeterminate form. Okay. Does that mean that the limit is non-existent? No, that doesn't mean that. Okay. That simply means that you have to apply another approach in finding the derivative. Now let's see. What can we do here? We're going to see if we can reduce this. The value that x is approaching, there might be a removable discontinuity there, which still indicates the existence of the limit, even though the function is not defined at that point. So let's go ahead and factor the numerator and the denominator. So the GCF in the numerator is x squared, so we'll factor that out. X squared, we're left with 5x squared plus 8. And then in the denominator, the GCF is x squared also. You have x to the fourth and x to the second power. Just simply grab the power of the smaller of the two. So x squared, and we're left with 3x squared minus 16. Okay, so what you notice is that we have a removable discontinuity at x equals 0, the number that the limit is approaching. Perhaps that's what caused us to get an indeterminate output, evaluating the function at the removable discontinuity. So this limit becomes, limit as x approaches 0. Now we've taken out the removable discontinuity. Let's see if everything is fine here. So now we can substitute. Okay, substitute again. We have 5 times 0 square plus 8 divided by 3 times 0 square minus 16. That leaves us with 8 over 16, negative 16. Final answer is negative 1/2. Answer to number 5 is option letter A.